Thank you, Hennis. Good afternoon, everybody. And I would like to say thanks to organizer to organize a nice meeting for invitation. I came from Dubna. You see that it's right place to study ultra-cold physics. This is a spring in Dubna. But our institute more known not researching of ultra-cold processes, but investigation of heavy ions and high-energy physics. But I will tell about our result in ultra-cold few-body processes. This result were obtained with a group of Peter, and some results were obtained in collaboration with Innsbruck group. This is outline of my talk. The speaker of this morning, they simplify my life, so I will not speak too much about why it's interesting, but just a few words about the method which we used, and I will concentrate on some results we obtained with this method. But nevertheless, I have to tell a few words about the setup. Setup was discussed this morning. We will concentrate on the such cigar-like traps and what happens in those traps. If atoms are in the trap, they are under the influence of the confinement of the trap, and we can approximate the interaction with the trap by harmonic oscillator, and the parameter of the oscillator for cesium atom like this. This is a trap width about 100 nanometers, and we have to consider some few-body physics. The simplest problem is two-body problem, but two-body problem special one. And we have to consider some peculiarities of this problem. First of all, we have to take into account the quantization in the transverse direction, what happens due to interaction with the trap. Then a more complicated problem, if it's two distinguishable particles, we have at least five-dimensional problem, two radial variables and three angles, and there is a mixing term which mix center of mass variable and relative variable. So it's a rather complicated problem, and we also have to include into consideration in elastic processes like molecule formation. The problem is interesting because this problem under control. We can control the interaction. Why this problem is interesting from the physical point of view, we have listened this morning, and I suppose in the talk of Selim Joachim, we also will listen to new results. So if the two particles interact in 3D free space and there is a near threshold resonance, by acting the external magnetic field, one can tune the interaction, and the interaction can be very strong, and this interaction one can describe with pseudopotential approximation by changing the magnetic field. Scattering length can be variated in a broad range, but if this two-body problem in the confining potential, this resonance is shifted. But in literature, this resonance has known like confinement-induced resonance, because in this place there is no resonance in free space, but in the confining trap there is a resonance. It's a famous result of Maxime-Olshany, which was obtained in quasi-potential approach. This slide I will skip, and let's go to the theory. And the simple theory was suggested by Maxim Olshany when he have considered two-body problem in pseudopotential approximation. This two-dimensional problem was projected to one dimension, and in this one dimension we have renormalization of interaction constant, and this constant has singularity at this point with respect to inverse value of the scattering length. This is a trap width. So near this point we have to observe some resonance behavior. In 3D space, free 3D space, we have no confinement, and if the scattering lengths cross zero, weakly bound state appear in the system. If you add the confinement, like this one, like Cigara one, the energy is shifted to the value h bar omega. And what is important, in quasi 1D harmonic trap, bound state exists for any scattering length, from negative scattering length to positive scattering length. This is a principal difference from the scattering in free 3D space. In free 3D space, the bound state exists only for the positive scattering lengths. But another peculiarity of scattering in the trap is appearance of excited level, and if excited level crossing the threshold, then we have this point of confinement-induced resonance, exactly in the point which was calculated by Maxim Olshany according to this formula. And in this case, interesting effect is appear, which is well known, so-called mapping of bosons to identical fermions. In this point, transmission coefficient goes to zero in the point of confinement-induced resonance. And its result was obtained in the pseudopotential approximation. But pseudopotential approximation has some limitation. For example, you can consider only S-wave scattering or only P-wave scattering, but cannot consider together S and P scattering and other limitations. So we have developed actually two computational schemes. One computational scheme is multi-channel scattering problem, two-dimensional one, and now we are working on three-dimensional one. And another one is splitting up method for time-dependent 3D and 4D Schrödinger equation. Those results were obtained because we have extended a famous discrete variable representation from 1D to 2D case. It's not trivial problem also was. So here some illustration of Hamiltonian for 4D quantum to body problem in quasi 1D harmonic trap. In this case, Hamiltonian has three terms. One term is center of mass motion, second term is relative motion, and there is a mixing term. Here is a mixing term. So if omega 1 not equal omega 2, if you consider scattering of two distinguishable particles, one cannot neglect this term. One cannot neglect this term, and problem becomes a non-separable one, at least four-dimensional. There is two radial variables, and there is two angles, phi and theta. So one has to solve this four-dimensional problem. And this program was realized. And we have considered 2D scattering, 4D scattering, multi-channel scattering in 1D trap, and those problems are in progress. So now some results. Here, first we have considered what happens with confinement-induced resonance at arbitrary colliding energy. Olshany has considered the scattering at zero energy. This is the energy in relative units. This is a threshold. This is a first excited threshold, second excited threshold, third excited threshold. And this is calculated transmission coefficient. And the black curve corresponds to Alshani case. One can see that here transmission coefficient equal to 0. But if we change the scattering length, if we change the interaction between the particles, so the position of the resonance is moving. Here, some resonance at non-zero colliding energy. And here, in this part, we present the probability density, which was calculated with our code as a function of zeta. Zeta is this direction, and transversal direction. First result, it's just we are before the resonance in this region. So if one can look in this transversal direction, one can see no nodes in this distribution, probability distribution. This is a case of resonance. In this case, the scattering is blocked, but two nodes appear in transversal direction. And then when we pass through the resonance, some scattering is possible here. And in the language of Feshbach resonance, it corresponds to the following. If we are below the resonance, so there is no nodes in the transversal direction. If we pass in the resonance, here two nodes appear. And then we have found a new effect in this system, so-called suppression of quantum scattering near confinement-induced resonances. This effect is possible if we replace the pseudo-potential but some real interaction where there is S-wave and D-wave states. And if such case appear in the 3D free space scattering, so we have the shape resonance, P-wave shape resonance, and background due to the S-wave scattering. But if we add the waveguide, so this P-wave resonance transform to the we called it dual confinement-induced resonance. Here, calculated repulsive coefficient has calculated, and you can see that here at this point the particles becomes transparent one to another. This is one effect what we have found. Another effect, resonance mechanism of molecule formation in quasi-1D trap with center of mass excitation. We have considered the collision of two particles, two distinguishable particles. In this case, one cannot neglect by the coupling of center of mass motion and relative motion due to this term. But initially, we just dropped this term by hand, and we decided to consider scattering of two particles when there is no coupling with center of mass. This is a bound state and two quantum numbers. This is a ground state. Ground state with respect to transversal excitation. First quantum number is excitation with respect to relative motion, and second quantum number is excitation with respect to the center of mass motion. In this case, we have calculated time evolution of the population of this state. One can see that when particles are approaching one to another, this state is populated. The population of the ground state is growing up, and then this state is decaying. It's a famous effect like back decay in molecular physics. And then we turn on this term, coupling of center of mass motion and relative motion, and due to this effect, we obtain the following. First, we see the population of the ground state. This is red curve. And then there is a transition from the ground state due to this term from the ground state to excited state. And we see this blue curve, the population of the excited state. And this is long-living state. Due to the back decay is forbidden. Direct back decay is forbidden. Back decay is possible only like two-step decay. And so because of this state is long-living. And here's the evolution of the probability density distribution as a function of time is given. Of course, it's a four-dimensional picture, but we did averaging over the angles and remaining variables. This is the relative variables and the variable of center of mass. And this is like the probability density distribution. It looks like after 1 time units. And then after 3 time units, you observe the population of the ground state. And after 8 time units, one can observe that we have the system in excited state with respect to center of mass excitation. And this is the case if we drop the interaction between center of mass and relative motion. Here you see there is no the molecule. This is a mechanism which we have considered, but the experimentalists so far did not observe this. Next result, it's D-wave resonances in atomic traps. It is well known that high partial wave interaction can lead to some novel many-body phenomena, such like unconventional superfluidity or superconductivity. But experimental task is big, how to observe very narrow D-wave resonance at zero energy limit. Another possibility is to consider polar molecules. There is this dipole-dipole interaction with anisotropic one, but the problem is that this coefficient dipole interaction is terribly small. We decided to consider another possibility for such anisotropy. We decided to consider this effect in the harmonic trap. In the harmonic trap, due to the interaction with the trap, we have this mixing of S wave and P wave. And such coupling may be rather strong and rather broad. One can demonstrate the transmission coefficient near such D-wave resonance in the trap. One can see that strong anisotropy is observed in rather broad region near the D-wave resonance. And we have calculated some dependence of shift of the S-wave scattering length when we add the trap. And we have observed that this ratio of this shift with respect to CS6, the diffusion coefficient, can be fit by straight line. It's some interesting effect. Finally, confinement splitting in 1D anisotropic harmonic waveguide. This result was obtained with experimentalist from Innsbruck, and the idea is the following. By varying the magnetic field, we can vary the scattering length. This is in 3D free space. And then in the trap, we have this picture, which I have already discussed. And in the experiment, if the system is near the confinement-induced resonance, such three-body triple collision can possible, and the energy release can be taken by the third particles, and molecule can form, and this third formation of the molecule near the resonance will lead to the increasing the atomic loss in the system. And such loss was analyzed for different frequency, but varying the frequency, we are varying the width of the trap, and experimentally they have observed this shift of the minimum of the atom in the trap. And if one can look to the dependence of the scattering lengths corresponding to those minimum. Actually, it's not minimum, but the edge of these curves, and fit this by straight line. And this straight line, exactly the straight line which was predicted by Olshany. So one can treat this result like experimental evidence of confinement-induced resonance. Then we decided to look what happened if it's not anisotropic trap in the transversal direction, if omega 1 not equal omega 2. What happened in this case? It is clear that the degeneracy of will be the degeneracy of the first excited state will be lived, and it's following from this simple picture that this state will be split up on 3 components, but one component, this one component, are not coupled with component third and component first. So the prediction was that experimentally they will observe 2 resonances in the case of anisotropy. And this is result for isotropic case, and this is result for anisotropic case. This result for anisotropic case. So anisotropy of the trap leads to the splitting of the confinement-induced resonance. And this result has stimulated theorists to develop further development of the theory. First 2 attempts were made with a pseudopotential approach, but in pseudopotential approach they did not observe the splitting. But it's clear because everybody knows that in delta function potential can support only one bound state. So this result was not so surprising. And because this result related with the splitting of excited state, we decided to extend our consideration for the multi-channel scattering. So we decided to consider the scattering from the initial transversal state to all possible excited state, and also to consider the scattering from excited state. And the effective transmission coefficient, it's the sum of partial transmission coefficient multiplied to the initial population of the states. And here the result of that partial transmission coefficient is given for the ground state and for the first excited state. First, for the case of isotropic waveguide. What this picture tells us? This picture tells us that the position of the minimum of the transmission coefficient from the ground state can be shifted with respect to the transmission coefficient from excited state. And this is effective transmission coefficient calculated for a few different colliding energy. But because the partial transmission coefficient from the ground state has very deep minimum, so the main contribution near minimum comes from excited state. So if the system initially even have 1 or 2% population of first excited state, then experimentalist can feel it near the confinement-induced resonance. It was our idea. So, and in reality, we see that if we comes to anisotropic waveguide, we see this appearance of 2 minimum in partial transmission coefficient from excited state. And what happens with effective transmission coefficient? We see that for 1% population of first excited state, we observe this splitting in transmission coefficient. And this splitting becomes more visible if the population is increasing. But necessary ingredient for this scheme for splitting of the minimum of the transmission coefficient is a population at least a few % of the transversally excited state. This is necessary ingredient. When we finish this paper, we have found a paper of Köstner and Duan, which when we have found such supporting words that if we consider pair collision near confinement induced resonance in the trap, it's usually leads to excitation of excited state. And also we did some calculation of transition probability near the confinement induced resonance, which also support us that near confinement induced resonance we always have a system in excited state. And there is, and here I would like to show how the spectrum looks like of two-body system in the trap. This is real calculation. Before I have shown you some scheme, but this is real calculated scheme, and we see that actually we for the excited level we don't see the crossing of the threshold, but we have we see some rearrangement of the spectrum. System goes this way and then jump from this point to this point, and new level appear in system. And this resonance jumping from this point to this point, and so all the system have rearrangement. So this picture not correct. And in the anisotropic trap we have such splitting of this state, and this part here we have the quasi-crossing, which is in agreement to the distance between the maxima of atomic loss in the Innsbruck experiment. But there is another scheme which explain this splitting. This scheme based on the fact that if we take into consideration unharmonicity, then we will have more complicated system. In addition to the harmonic spectrum, some unharmonic part is appearing. This is a calculation for its effect of center of mass coupling, but the same effect gives the unharmonicity term. So in addition to induced resonances, harmonic induced resonance, which was considered by Olshani and which we consider in our approximation, there is also unharmonicity part. And this unharmonicity part have been considered in the paper of Alexandro Zayens and in the group of Peter Drummond. And they have found that this unharmonicity part in good agreement with the distance between the maxima of the atomic loss in the Innsbruck experiment. But they neglect harmonic part. And so our point of view is that this problem is still uncompleted and demand other consideration. It's need to consider more carefully the population of excited state, velocity distribution over the collision energy, influence of inelastic channel of molecule formation for the shift of the resonance, shift and splitting of the confinement-induced resonance due to unharmonicity, and also tensorial structure of the interatomic interaction. What I mean here, it's need also to include the rotational and spin structure of the molecular state in the closed channel responsible for the Feshbach resonance, and also include the width of the Feshbach resonance. And also it's need to make this direct step from the scattering parameters to come to atomic loss. This also was not done. But part of this program we already have realized, this part, which I would like to discuss now. So tensorial structure of the interatomic interaction. What I mean? It is known that in the cesium atoms there are many Feshbach resonances, and here in this graph 3 Feshbach resonances are given: S-wave resonance, D-wave resonance, and G-wave resonance. Actually, Innsbruck group, they were working near these D-wave resonances. Olshani has considered simplified picture S-wave resonance. Yes, I see. And Innsbruck group, they were working near this resonance. And they have this resonance and nearby resonance, this one, and S-wave resonance have been analyzed in the two-channel scheme, which gives a good possibility to express the potential element of the two-channel potential through the position of the resonance width, and magnetic field corresponding to the resonance. We decided to extend this scheme for this scheme was applied in free space scattering. We decided to extend this scheme to scattering in the trap. First, we repeat, we include this 4-channel potential. Why 4-channel potential? Because first channel it's entrance channel, and 3-channel describes the Feshbach resonance of different tensorial structure. And with this potential, we repeat the fitting which was done in the paper of Planck. So we use those parameters in this paper, and we fixed the potential of our 4-channel potential, which describe interatomic interaction. And then we add the trap and did the calculation of the transmission coefficient and the function of external magnetic field. This is for calculation for the trap, and this is a calculation of Lange and et al. For the case of the absence of the trap, so for the scattering length in the free space. You see, for the S-wave resonance, we see this shift of the resonance. This is Olshani resonance, broad S-wave resonance, and 2 resonances, D-wave and G-wave resonances. Innsbruck group is working here, so we will look in this region in more detail. This is some result for near this resonance. It's transmission coefficient as a function of magnetic field for different omega, and we observe one maximum which is independent on the parameter of the trap, and we see this variation of the minimum of the transmission coefficient with variation of the trap frequency. The frequency is very close to the ones which were used in Innsbruck experiment. When we fit those minimum, we see that this minimum described very well by Olshani formula. So this is confinement-induced resonance, but what means this maximum? And we see that this maximum corresponds to the crossing of the scattering length, crossing of 0. And because scattering length equals 0 in this point, so this maximum is independent on the magnetic field. So I again return to this famous picture, which is very, which people who are working in this field very familiar with this picture. So this point, those points C correspond to appearance of confinement-induced resonance. This maximum point B correspond to appearance of new bound state. This point B corresponds this maximum, or the crossing of the scattering length crossing 0. And this point is Feshbach resonance, position of Feshbach resonance in free space. So this is in free space the appearance of resonance. everything is clear. And we have some unpublished data of Elmar Haller from Innsbruck group. This part was published, but this part was not published. Two stable resonance. Now we know what means this resonance. This resonance corresponds to the crossing of the scattering length, crossing the zero. But what with another peak? Here there are two possibilities. One possibility is appearance of the bound state in excited state, because our preliminary calculation shows that this point will be more close to this point than this one. Point B corresponds this point, but B prime close more this. Another possibility is some indication of appearance of the D-wave resonance, but it's not yet clear. We did not see any structure here. And last slide. Here we have calculated also the molecular state population as a function of magnetic field. Because we have this four-channel potential, we can calculate the population during the collision of this molecular state. This is a result for free space, mainly system R in the entrance channel. But then when we add the trap, we see that most dominant become the population of D-wave state, this blue line. Other population of other state, they happened due to non-resonant interaction, and they are much less. And final slide, we have present here the contour plot of this molecular state near this magnetic field, and one can see that this is obviously not S wave but D-wave state. And here I will miss this, and finally last slide. The improvement of the model can be done in this direction, including anharmonicity, inelastic channel, and then one can consider anisotropic scattering in waveguide, two-body problems in 2D traps and 3D traps, and three-body physics in the trap. And last slide. Many experiments are in the world, and they need some theory, but time for simple model is over. But we're ready for that. Thank you.